Welcome to episode 7 of IT 3000, where today we're unpacking one of the most fundamental ideas in operating systems, the process. Put simply, a process is a program brought to life by the operating system the moment static code stops sitting quietly on disk and starts actually doing something. Think of it this way: a program is a recipe written down and waiting. A process is dinner actually being cooked with heat, motion, and ingredients in play. So let's sharpen that definition. A process is an instance the operating system creates when it takes a program and starts executing it. And crucially, that instance comes with its own identity, a unique identifier, its own private slice of memory, its own open files and resources, and its own security context. And here's the key insight worth holding on to: the program on disk is passive, the process in memory is alive, and from a single program, the OS can spin up many independent processes, each one its own separate dinner cooked from the same recipe. So let's crack that instance open and look at the 4 things every process actually owns. First, its identity, a process ID, a parent ID, and a state, which is how the OS refers to it, and incidentally, how you kill it. Second, its address space, private virtual memory that the OS physically prevents other processes from reading. Third, its resources, open files, sockets, locks, all of which must be released when the process exits. And fourth, its security context, the owner and privileges that decide what it's allowed to touch. The OS bundles all 4 into one structure per process, called the process control block. Zoom in on that address space and every process sees the same tidy 4-layer map, no matter how much physical RAM the machine actually has. At the bottom sits the code, the read-only instructions, then the data segment for globals and statics, then the heap growing upward for anything allocated at runtime, and at the top the stack, growing downward with each function call. Between the heap and the stack lies a shared pool of free space, and when the stack grows so deep it collides with the heap, that's a stack overflow, quite literally. Now that we've mapped out where a process lives, let's watch how it actually behaves, because a process is rarely sitting still. It cycles through 5 states, often thousands of times per second. It's born in the new state, where the OS builds its control block and address space but hasn't run a single instruction yet. Then it moves to ready, fully prepared, standing in line for a free CPU core. When the scheduler picks it, it enters running, but only for a brief time slice before it's swapped out again. If it asks for something slow, a disk read, a network reply, it drops into waiting, sleeping without consuming any CPU until the answer arrives. And finally, terminated. The work is done or the process was killed, the OS reclaims its memory, and all that remains is a small exit code. Before we go further, let's clear up 3 words that often get tangled together in Task Manager. A process has its own isolated memory, expensive to create, but bulletproof in the sense that if one crashes, its neighbors keep running untouched. A thread lives inside a process and shares its memory, which makes it cheap and fast to spawn, but also means one misbehaving thread can bring the whole process down with it. And a service is simply a process that the system itself starts, not you, quietly running in the background, usually from boot all the way to shutdown. And each of those ideas deserves its own episode. Thread comes next, where we'll zoom inside a process and see how execution actually flows. After that, the scheduler decides who gets the CPU and when. Virtual memory explains how each process gets its own private address space, and daemons, IPC, and signals round out how processes live, talk, and react in a real operating system. So let's lock in the essentials. A process owns 4 things: identity, address space, resources, and security context. It moves through 5 states, and remember, waiting isn't slowness, it's a process paused for a reason. And the single line that separates processes from threads, isolation, is the one that shapes almost every design decision an operating system makes. A program is just a recipe, a process is the meal being cooked. See you in the next episode.